right, good morning. Let's get started here. So I asked you to try and find the formula for the volume of a frustrum, right? How'd that go?
Good.
It was frustrating getting the frustrum.
I think I know why they named that shape that.
Yeah. Okay, so if you have that for me, please pass it towards the center and I'll come pick them up. A couple of other administrative things. The video from last class, I uploaded it and then I forgot to publish it. So I'll publish that video after class and then I'll publish the video from today. And then I sent out a quiz yesterday through the Canvas email. Did y'all get that?
Yes.
It's the one about the pipes, right? So I'm asking you to find the volume of two intersecting pipes. And I think I hint in the email that you can use the cross-section method that we discussed in class. And then I say you can use your calculator or use Wolfram Alpha or something to calculate the integral. Really it's about setting up the integral to get the volume. Just so you know though, on that problem, let me bring it up here. Pipes. So on that problem, I'm asking you to find the volume of both of these pipes, right? And really the heart of the problem is trying to find the volume of the region that they both share, right? Because if you just get the volume of each pipe separately, right, then you're going to count that common region, you're going to count it twice, aren't you? That's an important thing that we need to understand, right? If you just give me two pipes, right, I can find the volume of those easily. But if I make them intersect, they have a common region that they share. And so if you can find the volume of that, you should be able to find the volume of the intersection. Do y'all have any questions on that? I mean, not like how to do it, but do you have any questions about, like, once you find this volume, do you know what to do once you've found that, or no? Because I'm not asking for the volume of that, I'm asking for the volume of both pipes together in that intersection. Do you know what to do? You're going to subtract something, right? You can find the volume of both pipes if they were separate. You can do that, and then you're going to subtract some, but are you going to subtract the whole thing? Okay, that's the part I want you to think about. How much of it are you going to subtract? We'll stop there. And then I showed you, that last picture was just to show you, like, maybe it's worthwhile for you to just look at finding the volume of that and then multiplying by 8. We talked about that last class. Okay, I said this is due Monday, and I said that's Halloween, right? And I said you can work together in the email I sent. I don't mind if you talk to each other. I don't mind if you come ask me for help. Just, don't go to the tutoring lab and be like, hey, I got to do this, I want you to see if you can help each other out, all right? All right, that's the first administrative, well, no, I talked about the video. Okay, so what are we doing today? We're going to start chapter 8, but I need to get some other stuff taken care of before that. Where'd it go? So what I've done is the notes that we have for the solids of revolution that I have online. We're using both washers and shells. I have nice color copies here. All right, and this also has the formulas for arc length and surface area. So this is pretty much all the formulas from chapter 7 that are important to us. I have copies for each of you. Problem is they're not all stapled. Okay, so what I'm going to do, think y'all can pull this off? I'm going to pass the stack around that's not stapled with a stapler, and you'll take, there's, I believe, 1, 2, how many pages are there? It's 3 pages. Take 3 pages, staple it, pass the stack down. Got that? Wait, did I not bring the stapler? No, I know I did. Did y'all see it? Well, maybe I didn't bring the stapler. Okay, take 3 and pass them down. All right? And I'll start this here. Take 3, pass them down. You'll have to staple them on your own time. And then these, I'll just pass these out in the back. 1, 2, 3, 4. 1, 2, 3, 4. There you go. Sorry, y'all are going to have to staple yours. Yes? Now, no, these are not allowed on the exam. Okay? These are not, but this is a good, I don't have one extra. But this is a good place to, just have a reference. All right? Yes? Well, when it comes around. Yeah, they'll come around. I have the last stapled on. All right? Okay, now, before we get in chapter 8, I'm going to leave this up today because I'm going to be working from my notes today because there's a ton of stuff here that will take way too long for me to write down on the board. Remember, all these notes are available to you in Canvas, right? Yes? All right, so I want to do one problem. It's a famous problem. Is that how you spell Gabriel? It is? Gabriel's horn. Okay, this is a famous problem. And you'll see why it's famous in a minute. So what we're going to do, we're not in chapter 8. Okay, we're still in chapter 7 here. What we're going to do is we're going to look at the function f of x equals 1 over x on the interval 1 to infinity. All right. So what does 1 over x look like if you graph it on 1 to infinity? Let's see. 1 over x. There's your graph. Oh, wait. I'm going to restrict the domain. X greater than equal to 1. So there it is. There's your graph, right? That's 1 over x from 1 to infinity. Goes forever. We could find the volume of this, right? Sorry, not the volume. We could find the area under this, couldn't we? We actually did this problem. If I asked you for the area under this, what would the integral be? If I asked for the area. Well, that's not on those sheets, right? This is just integral from 1 to infinity. And then when we want to do area, we just add up all the rectangles, right? So we need the heights times the widths. The height is just the function itself. And the width is dx, right? And if we do that, we would have to do a limit and all that stuff because we have an infinite limit of integration. We do a limit. And we did this problem, and we found that this diverged. Okay, if you go back through it, you'll get natural log, and then take a limit, and it goes to infinity. So basically what we find is that this goes to infinity, which means it diverges. Which means that this area under here is infinite, all right? That's not what we're going to talk about today. I just want to make sure you understand this is one thing we could ask, right, from that picture. What I want you to do instead of that is this. First, I want you to find the volume of the solid if we rotate about the x-axis. And then the second question I'll have here is I want you to find the surface area if rotated about the x-axis again, right? So I have a picture for you here. Maybe. So here's that same graph, right? What I'm asking you to do is wrap this thing around the x-axis, right? And you will create this shape right here, right? I want to know the volume of it. So if it was solid, right? Imagine that was a solid thing, then what would the volume of that solid be? And then the second question is, if you were to try and like paint the surface of it, what's the surface area? But you have to remember, this thing goes forever, right? That thing goes forever. Now they call it Gabriel's horn because it has to do with the angel Gabriel. I don't know, some theological thing here. There's an angel called Gabriel, named Gabriel. It's his horn. It's Gabriel's horn, this infinite horn. I don't know, I didn't make this up, okay? So this is the problem of Gabriel's horn. We're going to find the volume of Gabriel's horn. We're going to find the surface area of Gabriel's horn, all right? You ready to do it? Start with the volume. How do we do volume? So we'll do washers, right? We'll do washers because we're going to be taking this region, you know, from 1 down, right? We're going to be taking, wrapping it around the x-axis. And so our rectangles will look like this, right? We wrap around, that's good for a washer, right? What's the outer radius? The distance from the axis of rotation to the top of the rectangle, that's just the function, right? What's the bottom radius? 0, because it's just the x-axis, right? So if we follow the formula that you now have, right, we're looking at the first one there, right, the first box. It's the volume will be, so I'm doing part 1. I'll put V equals, because we're finding the volume, pi integral what to what? 1 to infinity. Okay, so we have an improper integral. And then the outer radius squared, which should be 1 over x squared. All I'm doing is squaring that function, or sorry, this function right here, right? Squaring it. And subtracting 0 squared, which is just 0. So this is it right here, right? Now, can somebody look in their notes? Did we do that integral in our notes? I don't want to have to redo it. I'm pretty sure we did. I just want to make sure someone sees it. When we were doing improper integrals, this would be improper integrals. Do you remember doing it? What is it? 6.6? Yeah, 6.6. Do you see it there? Yes, you do? Yeah? What example did I do right before it? I probably did 1 over x right before it, or maybe, you got it? It's there?
Yes, the first example you did.
It's the first example I did. Oh, great. Okay, good. And what did we get as an answer? We got 1.
Yeah.
Okay, so I'm not going to do this work because I already did it in our notes, all right? So that integral right there turns out to be 1. And then you have times pi, right? So your answer is just pi. Huh. Weird. Gabriel's horn has as a volume pi. So if you wanted to define pi, you could define pi this way. If someone said, hey, what's pi? You could say, well, it's the volume of Gabriel's horn. You could, right? Yeah? All right. We good so far? All right, let's do the second thing. Now what I want is the surface area. So for surface area, that's not what I just erased, right? It's not the area under the curve. It's wrap the surface or wrap the curve around and find the surface area. That's a formula from last class, which is now in front of you, right? I have this here. Which one is this? So look at the page that has lines on it. 7.3, area of surface of revolution. We have an x-axis rotation, right? That's what we have. An x-axis rotation. And in this, on this sheet, I give you 2 scenarios. Either you have a function of x, or the second one on the bottom is you have a function of y. What do we have? Function of x, right? So we're going to be using this formula right here. I'm just going to write the formula down first. It's 2 pi the area will be 2 pi integral from a to b of f of x, whatever the function is, times the square root of 1 plus whatever the derivative of the function is, that quantity squared dx. I developed that formula in class on Monday, right? I came up with that formula. Remember the rubber band, right? And then I actually proved the surface area of a sphere, right? That's what we finished class with, I think. So that's the formula I'm going to use, right? So to use this formula, what I'm going to do is I'm going to do some scratch work on the side. I'm going to figure out what the derivative is first. Okay, so what's the derivative of this function? Derivative of that would be negative 1 over x squared, right? Because this is really like x to the negative 1, and then bring the negative 1 out, subtract 1, so it'd be x to the negative 2, and then I can rewrite that as this. Is that too much to ask? You all are good? That's a derivative. And then I need to, in the formula, I'm going to need to square it, right? So I'm going to square that. So if I take that and I square it, it just becomes 1 over x to the 4th, right? 1 over x to the 4th. And then I'm going to add 1 to it, right? So I think I'm ready to put this integral together. I'm going to do 2 pi integral 0, I'm sorry, not 0. We're not going from 0. That would be a problem. 1 to infinity. Now, the function itself, right? The function itself, which is 1 over x. Okay? And then times 1 plus 1 over x to the 4th dx. That's the integral I'm trying to find. Follow it? Now, we can sit here and suffer with this integral. This integral is extremely difficult to do, all right? In fact, we have no method for this, all right? Even though it may look like maybe you can simplify it. I mean, there's nothing, when I look at this right off the bat, it's not like I just go, oh yeah, I can't do that. I'm just telling you, like, if you try it, you're not going to get it, all right? There's nothing that just like tells you that. You would have to suffer with it for a while and then give up at some point. One way you could check that you're not going to get it is to go to like Wolfram Alpha or something like that. Let's try it. Let's just go and let's just ask for the antiderivative. Okay, the antiderivative of 1 over x times the square root of 1 plus 1 over x raised to the 4th power dx. And let's see if it can even find an antiderivative. My guess is it's going to bring in some error function or elliptical function. Oh, well, how about that? All right, well, the computer was able to do it. All right, that's good. We're not going to, though, okay? We're not going to do that. And here's why, because I know what the answer is. I know where this is headed, all right? So I'm going to do something I've never done in this class. I'm going to have you consider something. This right here is some function. I'm going to call it capital F of x so that you don't confuse it with this one, all right? Yeah? Forget the 2 pi, okay? Just look at this right here. Would you agree that this is saying, hey, go find the area underneath that function from 1 to infinity? That's what this integral would mean if you looked at this kind of like separate from where it came from. If this is some capital F function, then this integral represents the area from 1 to infinity underneath that curve. Y'all buy that? Yeah. Okay. What I want you to see now is this. That capital F of x, that function right there, do you agree with this? It's bigger than or equal to 1 over x. Why? Why is this bigger than 1 over x? Because this piece right here in blue, right? This number right here, or this value, whatever it is, 1 divided by x to a power, as long as x is a positive number, 1 divided by x to the 4th power there, that should be a little number, right? Or some number, it should be something, right? And if I add 1 to it, that's bigger than 1. So what's in blue here is bigger than 1, right? So if I take a number that's bigger than 1 and I multiply it by 1 over x, this whole thing should be bigger than 1 over x, right? Because I'm taking 1 over x and multiplying by something bigger than 1. Follow? So this capital F of x should be bigger than that, right? So if this is bigger than this, then do you agree that the area under this is bigger than the area under this? Right? Remember, I was saying this integral represents the area under this function from 1 to infinity. Using what I just had on the board, what we can say is this: 2 pi integral 1 to infinity of 1 over x square root of 1 plus 1 over x to the 4th dx must be greater than or equal to 2 pi integral from 1 to infinity of just 1 over x dx. Because this is bigger than that. So the area under this should be bigger than the area under that. You still buy that? Yeah? But what's this? Infinity. Right? And so this has to be bigger than or equal to infinity, which means this has to be infinite. Okay? What does that mean? The surface area is infinite. We call this the paradox of Gabriel's horn. Why is it a paradox? What have we said? We said that the volume of Gabriel's horn is what? Pi, right? And we said that the surface area is infinite. So you can take Gabriel's horn, okay, and you can fill it with pi liters or whatever unit you want to use. It has a volume, right? How much it holds. But it's impossible to paint its surface because it would require an infinite amount. It has an infinite surface area. Is that not paradoxical? Paradox? How do I say it? Paradoxical? Paradoxical, right? Is that counterintuitive? I mean, if you fill it with something, haven't you essentially painted the surface? Kind of? Yeah, I don't know. It has to do with the fact that when we talk about surface area, when we do in the real world, we're actually, like when you go to paint the walls of a room, right? And you go look at the gallon of paint and it says, oh, this will cover approximately 300 square feet, right? Well, that's assuming there's a certain thickness to the paint, right? So when you put paint on a surface, it's actually three-dimensional. It's a volume you're actually doing, right? But when we think about surface area, we think of it like in mathematical terms. We think of it in a different way than we think about it in the real world. Here's the best, I guess, if I'm going to try and explain this. If I give you a point in space, okay, so imagine you have a sheet of paper, here we go. I give you a point in space. How thick is that point? Mathematically, 0. It has no thickness. But on this sheet of paper, I can measure how wide that is, right? But in the theoretical sense, it has no width to it, right? Just like if I take a line segment, right? I can measure how long it is, but how thick is the line? Mathematically, 0. It has no thickness. If I take a surface, an area like that, I can measure the area, right? How thick is this though? 0, right? It doesn't come out at you at all. But we know if you hold a sheet of paper, it has a thickness, right? I'll stop there. So when we are talking about surface area here, right? It's assuming a thickness of nothing, where paint for us doesn't have a thickness of nothing. I hope that kind of makes sense. All right, I just wanted you to see that problem because it's an interesting problem and it uses a lot of the things that we've learned, right? How to find a volume, how to find the surface area, how to find the area, how you can compare two integrals like that, how I did that. That's something that's useful. If you can ever do that, it's useful. All right, chapter 8. We ready? No questions? Are there any leftover pages there? No? You'll just put them around. So we made it. Chapter 8. Sequences and series, all right? I know you've heard horrible things about this, but it's doable. It's just going to be a lot, all right? So buckle up. Lots of definitions to begin this chapter. This chapter is called Sequences and Series, and we're going to start with this idea of sequences. But before I start, how about some motivation in terms of like where are we going to go with this, right? Where are we headed with this? And I've alluded to this a little bit earlier in the semester. Let's say we're going to take a look at a function that we're familiar with, all right? Let's say we want to take the graph of e to the x, all right? We all know what e to the x looks like, yes? Now, e to the x is definitely not a straight line, right? It's not a parabola. This is not a polynomial function, is it? The question is, can I approximate this function, approximate it with a polynomial? Is it possible for me to create a new function that would be a polynomial function that would be kind of close to what this one is, all right? Now, you're going to sit here and ask, why do I want to approximate? We have the function, right? Why would you ever want to approximate that? You'll see why in a minute, all right? So here's what we know. I know that at the point 0, the function spits out 1, right? I know that about this function. That means if I'm going to try and come up with a new function, I'm going to call it g of x. This is some new function. New approximate function. I would like for that function g to also pass through that point, right? So for this function that I'm trying to come up with, I want g of 0 to also be 1, right? I want g of 0 to also be 1. And then at least they would match at one point, wouldn't they? Okay. What else could I want to happen? Match at more than one point, right? More than one point. That's one approach, okay? But we're going to do it slightly different. What we're going to do is we're going to start using what we know about calculus. So if we want g to look like this function, right? If we want them to look the same, then at 0 we want them to be the same. And don't we want the slope of the tangent line there to also be the same? So wouldn't we like g prime at 0 to be equal to whatever the derivative of this is at 0? What is the derivative of this function at 0? So first, what's the derivative of that function? E to the x. Okay, so what's the derivative of that function at 0? 1 again, right? So whatever function we're going to come up with, okay, I don't know what it is, not only do we want, when you plug 0 into the function that you get 1, we want that when you plug 0 into the first derivative, you should also get 1 as well, right? Then not only would they both match at this point, they would both go through that point, but they would both have the same slope of a tangent line there, wouldn't they? Hey, couldn't we make the second derivative match as well? Wouldn't it be nice if the second, because second derivative is concavity, right, from Cal 1? Wouldn't it be nice if they both had that same concavity shape? Okay, well, then why don't we see what's the second derivative of this function? E to the x. Do you see why I chose e to the x for our first function here? Because it's easy to take derivative, right? So what's the derivative at 0? 1 again, right? So we would want our function over here to also have that same derivative, right? And I could keep doing this, couldn't I? I would like the third derivative to be the same, the fourth derivative, fifth derivative, sixth derivative, seventh derivative. So I want all my derivatives to be the same value as the derivative over there, and since that's e to the x, you're going to get 1 each time, aren't you? So all of these derivatives need to be 1. I need the function at 0 to be 1, I need the derivative at 0 to be 1, the second derivative at 0 to be 1, third derivative, fourth derivative, fifth derivative, and so on and so forth, yes? Okay, so let's try and see if we can't come up with a function. We could try a line, but I think a line's going to suck. We could do a parabola, couldn't we? Maybe? Try and fit a parabola on here? Let's try a parabola. So I'm going to guess a function. And it's going to be a parabola. ax squared plus bx plus c. All right? This is a generic parabola function, right? I just need to figure out what a, b, and c are. Well, let's use this first piece of information. If I plug 0 into that function, I need to get 1. What does that tell you? That tells me c is 1, right? If I plug 0 into this, I get a times 0 squared plus b times 0 plus c, but that must equal 1 because I want when I plug 0 in to get 1, that would force c to be 1, right? So now I know from this that c is 1. Okay. Now I want the derivative at 0 to be 1. So can you take derivative of that? What's derivative of that? I'll just put it over here. What's g prime of x? 2ax plus b, right? 2ax plus b. And we want that when we plug 0 into that, we get 1. So when you plug 0 into this, 2a times 0 plus b, you should get 1, which means b should be what? This is going to be 0, right? That's 0. So b should be 1 again, right? b should be 1. And then I want what? The second derivative at 0 to be 1. So what's the second derivative? 2a. And when I plug 0 into that to get 1, well, look, there's no x's in here anymore, are there? So plug in 0 doesn't change that. That means a has to be a what? 1/2. There we go. Now, if I continue, this is going to be what? Next derivative? 0. And then 0 and 0. And so for the rest of the way, I'm never going to be able to make it match, right? But I've come up with, by using a quadratic function to approximate this function, I have come up with a quadratic that's at least going to match at 0, I'm going to get 1, the derivative is going to match, and the second derivative is going to match. After that, nothing will match. Can we write the function now? What is g? A was what? 1/2 x squared plus b, b was 1, plus x plus c, c was 1, right? So now what I'm going to do is I'm going to go to Desmos, and I'm going to graph first e to the x. There's e to the x, right? And now what I'm going to do is I'm going to graph what we just came up with. 1/2 x squared plus x plus 1. What do you think? Good approximation?